Hello, my name is Chen Fanra and my matrix number is 178767. My partner is Hani and Katie. We would like to explain about the light propagation in optical fiber. So first of all, for my part, I will explain about the visible light and the Snell's law and the total internal refraction. The first thing I want to explain about this figure is optical spectrum. You can see that the visible light extends from 380 nanoviolet to 780 nanometer nm rate. So for a smaller wavelength, ultraviolet radiation UV occur. For the longer wavelength corresponding to infrared region IR. Optical fiber communication elements operate in the micrometer wavelength zone of the frequency spectrum, frequency between 10 power 14 Hz to 10 power 15 Hz. Next, I want to talk about light propagation with velocity c equals to 3 times 10 power of 8 meter per second. In a transparent medium, the speed of light is affected by a factor n. This n. N is the refractive index of the medium. The formula of n is n equals to speed of light in free space over speed of light in the medium. The next is the Snell's law. When a light ray encounters the interface of the medium, like this, the light ray is refracted and its direction of the propagational change according to the Snell's law refraction. It will go down. It will refract to other surface. The Snell's law is n1 sine theta 1 equals to n2 sine theta 2. So this figure already show the Snell's law, how the light goes to n2 surface. If theta 1 is less than theta 2. For the next case is if n1 is greater than n2. What will happen? It is like at a certain angle of incidence, the refracted wave propagate parallel to the interface. This line is parallel to the interface, and the angle of refraction reach 90 degree. This one 90 degree, and the corresponding angle of incidence is called the critical angle. This will become the critical angle, and this is 90 degree and parallel to the interface if n1 greater than n2. For the next case is if the angle of incidence is greater than critical angle. For angle of incidence which is greater than critical angle, the rays are totally reflected like this. It's nice. No light has refracted and go to the n2 surface. So it's totally reflected. So this is total internal reflection. That's all for me. My partner Katie will explain about the acceptance angles for the next part. Thank you.
Let's discuss on the acceptance angle in light propagation. Actually, what is the acceptance angle? Acceptance angle is shown by here. Acceptance angle is actually the maximum incidence angle which allow the light to propagate in the fiber. Means any incidence angle less than the acceptance angle is not allowed to propagate in the fiber. So it can be seen that a ray that meets the first core cladding interface at the critical angle. This ray essentially meets the fiber core at an incidence angle of A, showing here. This incidence angle is defined as the acceptance angle of the fiber. Any light rays incidence at the fiber core with an angle greater than the acceptance angle will not be allowed to be reflected sufficiently to undergo a total internal reflection at the core cladding interface, and therefore they will enter the core. They will be allowed to enter the core, but they will not be accepted into the fiber for onward transmission. So actually acceptance angle is measured in the air outside the fiber. Actually, numerical aperture is closely related to the acceptance angle. It's given by the formula here. The numerical aperture is equal to the psi of acceptance angle. And it's also another formula is given by the square root of n1 squared minus n2 squared. The n1 is a refractive index of core, whereas the n2 is a refractive index of cladding. Showing here, this optical fiber has the bigger numerical aperture than the below one. The numerical aperture actually is used to measure the light gathering ability of a fiber.